You can see it with your naked eye on a dark night, a faint smudge in the constellation Andromeda, the Andromeda Galaxy, our nearest large galactic neighbor, 2.5 million light-years away. It contains 1 trillion stars. It's beautiful, it's majestic, and you will never reach it. Not you personally, not humanity, not any civilization we could ever build. Not even if we had millions of years and technology we can barely imagine. Andromeda is forever out of reach. Not because it's too far, not because we can't build fast enough ships, but because the universe itself is expanding. Space is growing between us and Andromeda. And that expansion will eventually make Andromeda unreachable. Not just difficult to reach, impossible. Fundamentally, physically impossible. I'm Leonard Susskind, and I've spent 50 years thinking about cosmology and the expansion of the universe. And I'm going to tell you why Andromeda, visible in our night sky, close enough to see with the naked eye, will eventually be forever beyond our reach. And what that means for the ultimate fate of everything. Let me start with the numbers. Andromeda is 2.5 million light-years from Earth. That means light from Andromeda takes 2.5 million years to reach us. When you look at Andromeda, you're seeing it as it was 2.5 million years ago, before humans existed. Before our genus Homo even evolved, you're looking into the deep past. Now, Andromeda is actually moving toward us, not away, toward. It's approaching at about 110 kilometers per second. This is unusual. Most galaxies are moving away from us because of cosmic expansion. But Andromeda is close enough that local gravity dominates over expansion. We and Andromeda are gravitationally bound, falling toward each other. In about 4 billion years, Andromeda and the Milky Way will collide. They'll merge into a single elliptical galaxy. This is inevitable. The collision will be spectacular, but not dangerous. Galaxies are mostly empty space. Stars are so far apart that stellar collisions will be rare. The galaxies will pass through each other, interact gravitationally, and eventually settle into a new configuration. Astronomers call it Milkomeda, or sometimes Milkdromeda, a merged galaxy containing all the stars from both spirals. So Andromeda is reachable, right? We're falling toward each other, we'll merge, eventually we'll be part of the same galaxy, yes. In 4 billion years, assuming we survive that long, we'll be neighbors with Andromeda's stars. But here's what people miss. The collision happens because we're gravitationally bound now. We're within each other's gravitational influence. Gravity pulls us together faster than expansion pulls us apart. We're a bound system. But this is rare, almost unique in the observable universe. Every other large galaxy beyond our local group is receding, moving away, accelerating away because of dark energy, and those galaxies will never be reachable. Let me explain why. The universe is expanding. Edwin Hubble discovered this in 1929. Distant galaxies are redshifted. Their light is stretched to longer wavelengths. The farther a galaxy is, the greater its redshift, the greater its recession velocity. This is not because galaxies are moving through space. It's because space itself is expanding. The fabric of space-time is stretching. Galaxies are carried along with the expansion. For decades, cosmologists assumed the expansion was slowing down. Gravity from all the matter in the universe should decelerate the expansion. Maybe it would eventually stop and reverse, leading to a big crunch. Or maybe it would continue forever, but slow down asymptotically. But in 1998, 2 teams discovered something shocking. The expansion is accelerating. Not slowing, accelerating. Distant supernovae were dimmer than expected, farther away than they should be if expansion were decelerating. The universe is speeding up. This acceleration is driven by dark energy. a mysterious component of the universe. With negative pressure, dark energy makes up about 68% of the total energy density of the universe. We don't know what it is, we don't know why it exists, but we know it's there and it's causing space to expand faster and faster. The simplest explanation is that dark energy is the cosmological constant, the constant energy density of empty space. Einstein introduced this in 1917, then abandoned it, but observations suggest it's real. Space has intrinsic energy, and this energy pushes space apart. Because of dark energy, the expansion of the universe accelerates. Distant galaxies recede faster and faster, and here's the crucial point. There's a distance beyond which galaxies recede faster than the speed of light. Not because they're moving through space faster than light. That would violate relativity. But because space between us and them is expanding fast enough that the total recession velocity exceeds light speed, this distance is called the cosmic event horizon. Currently, it's about 16 billion light years away. Galaxies beyond this horizon are receding faster than light. Light they emit now will never reach us. Not ever. Not in infinite time. Because the space between us and them is expanding faster than light can cross it. The light tries to reach us, but space expands faster. The light makes no progress. It's like swimming against a current faster than you can swim. You can swim forward, but the current pushes you back faster. You never make progress. Light from beyond the horizon never reaches us. And conversely, light we emit now will never reach those galaxies. We are causally disconnected forever. This is not hypothetical. This is happening now. Now, here's the key realization. The cosmic event horizon is shrinking, not in physical size, but in co-moving coordinates. As time goes on, more and more galaxies cross the horizon. Galaxies that are currently visible will eventually become invisible. They'll recede beyond the horizon. We'll lose them forever. And it's not just that we'll stop receiving new light from them. The light that's already on its way to us will redshift to longer and longer wavelengths. Eventually, the wavelength becomes infinite. The light loses all its energy. It effectively disappears. The galaxy fades from view. In a few trillion years, almost all galaxies outside our local group will have crossed the horizon. The night sky will be mostly empty. Just the merged remnant of the Milky Way and Andromeda and a few dozen smaller galaxies in our local group. Everything else will be gone, invisible, unreachable. This is the future of the universe, cosmic isolation. Let me make this concrete. Right now, we can see galaxies that are 46 billion light years away. This is the radius of the observable universe. How can we see galaxies 46 billion light years away when the universe is only 13.8 billion years old and light can only travel 13.8 billion light years? Because space has been expanding while the light was traveling. Light from a galaxy emitted 13.8 billion years ago has been traveling for 13.8 billion years. But during that time, space expanded. The galaxy is now 46 billion light years away. We can see it, but we're seeing it as it was 13.8 billion years ago. If we look at the cosmic event horizon, it's currently about 16 billion light years away. Galaxies at this distance are right at the edge. Light from them barely reaches us. Galaxies beyond this are invisible. Now, as time passes, the horizon doesn't expand. Because of accelerating expansion, it stays roughly constant or even shrinks in co-moving terms. Galaxies that are now inside the horizon will eventually cross it. We'll lose them. The observable universe is shrinking in terms of what we can actually see. Let's calculate how long it would take to reach Andromeda. If we could travel at the speed of light, it would take 2.5 million years. But we can't travel at the speed of light. With current technology, Voyager 1, our fastest spacecraft, travels at 17 kilometers per second. At that speed, it would take about 44 billion years to reach Andromeda. 44 billion years. For comparison, the universe is currently 13.8 billion years old. By the time we reach Andromeda at Voyager speed, the universe will be more than 4 times its current age. The sun will have been dead for 39 billion years. Long dead. Earth will have been destroyed. The Milky Way and Andromeda will have already merged. There won't be 2 separate galaxies anymore, just one merged galaxy. So the notion of traveling to Andromeda as a separate galaxy makes no sense on these timescales. But let's be more optimistic. Suppose we develop much faster propulsion. Suppose we can reach 10% the speed of light. This is far beyond our current capability, but not impossible in principle. At 10% light speed, the journey to Andromeda would take 25 million years. Still unimaginably long. Longer than complex life has existed on Earth. Longer than our species will likely survive. But let's suppose a civilization lasts that long and builds generation ships. Could they reach Andromeda? Maybe, if they left now. But the key point is that Andromeda is special. It's one of the only large galaxies we could possibly reach, even in principle, because it's gravitationally bound to us. It's not receding. Almost every other galaxy is receding and accelerating away. Let me give you some examples. The Sombrero Galaxy is about 30 million light years away. It's receding at about 1,000 kilometers per second due to cosmic expansion. At 10% light speed, we could never catch it. It's moving away faster than we could travel toward it. Well, not quite. With continuous acceleration, we might catch up, but the energy required would be enormous. And as time goes on, the recession velocity increases, dark energy accelerates the expansion. Eventually, Sombrero will cross the cosmic event horizon. It will recede faster than light. At that point, reaching it becomes impossible. No matter how fast we travel, we can't catch something receding faster than light because space itself is expanding. The Virgo cluster is about 50 million light years away. It contains thousands of galaxies. It's receding at about 1,200 kilometers per second. By the time we could travel there, it would have receded much farther. It's already borderline unreachable. The Coma cluster, 300 million light years away, is definitely unreachable. It's receding at about 7,000 kilometers per second. Even traveling at near light speed, we'd never catch it. It's moving away too fast. And its recession is accelerating. Now let's talk about the most distant galaxies we can see. The most distant confirmed galaxy is currently about 13.4 billion light years away in light travel distance. We're seeing it as it was 13.4 billion years ago, just 400 million years after the Big Bang. Due to expansion, it's now about 33 billion light years away in comoving distance. And it's receding at several times the speed of light. It's far beyond the cosmic event horizon. We can see it because the light was emitted long ago when it was closer and within the horizon. But we can never reach it. And we'll eventually stop receiving light from it. In the far future, it will fade from view completely. This galaxy is forever unreachable. So here's the stark reality. Of the trillions of galaxies in the observable universe, almost all are unreachable forever. We can see them, we can study them, but we can never go there. The only galaxies we could possibly reach are in our local group, the Milky Way, Andromeda, Triangulum, and a few dozen dwarf galaxies. These are gravitationally bound. They're not being pulled apart by expansion. Everything else is receding. And most of it is receding faster than we could ever travel. We are trapped in our local group forever. Let me tell you what this means for the far future. In a few trillion years, star formation will cease. The gas clouds that form stars will be exhausted. The last stars will be born. These will be small red dwarfs that burn for trillions of years, but eventually, even they will die. The universe will enter the degenerate era. No more stars, just stellar remnants. White dwarfs, neutron stars, black holes. And by that time, the observable universe will be tiny. Just our local group, the merged remnant of the Milky Way and Andromeda, a few small galaxies, and darkness, empty space in all directions. Future civilizations, if they exist, will look out and see almost nothing. No distant galaxies, no cosmic microwave background. That will have redshifted to infinite wavelength and disappeared. Just a few nearby galaxies in darkness. They won't even know the universe is larger. They won't be able to see evidence of the Big Bang. They won't be able to measure cosmic expansion because there's nothing distant to measure. They'll think the universe is just their local cluster. They'll be cosmologically ignorant, trapped in an island with no knowledge of the ocean beyond. This is the future, cosmic isolation. Now, let me address a question. What about wormholes? What about faster than light travel? What about warp drives? Could these technologies allow us to reach distant galaxies? The short answer is no. Wormholes, if they exist, require exotic matter with negative energy density. We've never observed such matter. Quantum field theory suggests it might exist in tiny amounts, but not enough to create traversable wormholes. And even if you could create a wormhole, you'd need to place one end at the destination. You can't use a wormhole to reach a place you've never been. You have to get there first, slowly, and then place the wormhole mouth. So wormholes don't help with the expansion problem. Warp drives, like the Alcubierre drive, are theoretical solutions to Einstein's equations that allow faster than light travel. But they also require exotic matter, and they have causality problems. And the energy requirements are absurd. The mass energy of a planet or more, even if theoretically possible, they're practically impossible. There's no way around the cosmic horizon. Once a galaxy recedes faster than light due to expansion, it's gone. No technology can reach it. This is a fundamental limit imposed by the geometry of space-time itself. Let me end with the philosophical implications. We live in a brief window of cosmic time, when the universe is visible, when we can see distant galaxies, when we can study the cosmic microwave background, when we can measure the expansion, when we can understand cosmology. In the past, less than 1 billion years after the Big Bang, the universe was too hot and dense. No stars yet, no observers. In the future, trillions of years from now, the universe will be too empty and dark. No distant galaxies, no cosmic background, no evidence of the Big Bang, just isolated clusters in a void. We live in the era when cosmology is possible. When the universe reveals itself, this window is temporary, brief on cosmic timescales, and within this window, we're discovering that almost everything we see is unreachable. We can observe but not visit. We can study but not touch. We're like prisoners in a cell with a window. We can see the world outside, but we can never leave. Andromeda is our cellmate. We'll merge with it. We're stuck together. But everything else, all the trillions of galaxies we see, they're beyond the walls, forever. After 50 years of studying cosmology, I find this both beautiful and tragic. Beautiful because it shows how special our moment is. We exist at a time when the universe is knowable. Tragic because it shows our limits. We're a curious species. We want to explore. We want to reach beyond. But the universe has boundaries, not walls you can touch, but boundaries in space-time itself, horizons we can never cross, distances we can never travel. Andromeda is 44 billion years away at our current speed, an impossible journey. But even if we were faster, almost everything else is receding beyond reach. We are islanders on a small cluster of galaxies in an expanding ocean. We can see distant islands, but the ocean is growing. The currents are too strong. We can never cross. We're home forever. Thank you for watching. Now you know why Andromeda will always be out of reach. Welcome to Cosmic Isolation.